Okay, so this is the 10th of the BGA Early Career Groups series on the Manual of Geotechnical Engineering, second edition. We're going to be discussing some chapters related to principles of design and verification in geotechnical engineering, with a focus on shallow foundations. So we've got three speakers tonight. First of all, we will have, I think, Christina Mavrommati. So Christina is a chartered geotechnical engineer with over 24 years of experience in the design and delivery of a wide range of large civil engineering works in the UK and Greece. Over the past 10 years, she has worked as a designer and team leader on major projects such as HS2, Crossrail 2, Doha Metro major stations, Thames Tideway Tunnel, and the Network Rail Wessex capacity upgrade. Currently a technical director within the Foundations and Geotechnics team of Mott MacDonald, Christina is making significant contributions to construction and the engineering industry through delivery of complex mega projects and managing geotechnical design teams. Tony O'Brien. Tony has 40 years international geotechnical and foundation engineering experience for transportation, building, nuclear, energy and water sector projects. He has led geotechnical design teams through all project phases from concept to detailed design and construction, and acted as chief client advisor during independent reviews and due diligence studies. He is regularly an expert witness during litigation and provides expert advice for post-failure forensic investigations, during dispute resolution and for insurance claims. A fellow of the Royal Academy of Engineering, Tony also leads the geotechnics practice globally within Mott MacDonald. And Manos Papadantonakis is a senior geotechnical engineer with over 8 years of professional experience in geotechnical and civil design, as well as construction phase support. He has contributed to both large-scale infrastructure developments and smaller civil engineering projects, providing technical excellence across diverse environments. His portfolio includes major infrastructure projects, where he played a key role in foundations, earthworks, and underground structures construction support. So we're going to hand over to Christina to start. We'll have 3 presentations and then we'll finish with discussion, Q&A and discussion. Thank
you. Right, so our presentation is split in 2 parts. Part 1, which focuses on chapter 2 and chapter 9 of the manual, will be me talking. And then part 2, which is about foundation types and conceptual design principles and shallow foundations, with some reference to settlement and stress distributions and bearing capacity theory, will be covered by Tony. And then at the end, Manos will give some examples of actual verification of design considerations on site. Okay, so the foundations and other geotechnical elements in context. Obviously, the contents of the manual cover quite a few things. I'll focus on a few of those. As you can see on the screen, highlighting a new addition to the chapter, which talks about design in a time of climate and biodiversity emergency. Okay, so geotechnical elements. Why is it that we we love working in this field, and we think it's unique, right? The geotechnical elements can be heavily loaded. Their installation process is not simple at all, and most interestingly, their capacity is very dependent on the ground, right? And the ground, as we very well known, can be not well understood. It is heterogeneous and hazardous. So, and assuming we get that right, then the capacity is influenced by the method of construction as well. So geotechnical elements have a generally a higher risk of failure. Hence, soil structure interaction needs vital consideration. You've got an example of a box buried underground, like it's very much dependent on how the earth will put pressure on it and how it will react to the loads. It's not just about how the structure will react. And then you need to think about different combinations of stiffnesses and strengths. You can see from this little graph that you can have a lot of different combinations of, a low stiffness response with high strength, but equally, a high stiffness with a low strength. Key requirements of geotechnical structures and elements: they must not fail, they must not move excessively, and they must last as long as intended in terms of their design life. So different modes of failures, which you probably have heard of before. This is like a brief revision, if you like. We talk about ultimate limit state, where we do bearing capacity checks, and then serviceability limit states, where we focus on the formations and settlements. Typically for foundations, for shallow foundations, and Tony will go into more detail later on that, there's the traditional kind of initial check that we do is to achieve a factor of safety of 3 against bearing capacity failure. And then we know empirically that this means that settlement will also be lower. However, we often need to go into a bit more detail than that, because it could lead to over-conservatism. And the little picture on the bottom right shows what the different failure of a ULS versus an SLS could look like in reality. Okay, so we're at a time where we cannot think about climate and biodiversity. This little graphic really depicts what things that we need to think about when we are looking at geotechnical designs. We have to think about circular economy, refurbishment and reuse of foundations. You probably hear this often, and integration with nature, as well as carbon reduction and resilience and adaptation of our structures in the future. There's more on that in chapter 11, which I think has been covered in a previous session. Right, so every project will go through distinct phases. We have the planning, development, implementation, operation, and decommissioning, and then we might go over that again. In the geotechnical design and the construction cycles, we start with our data, which then informs design, which then allows construction. But at every stage, we can go back a loop, do another iteration with alternative design, or readjust designs because the construction process or the construction method could influence those design parameters and the approach we do. All that then goes back to how the data can influence the choice of the construction method. So no stage is kind of independent of the other one. Right, so interaction with other professionals. Contrary to popular belief, especially in this room and online, we are not the most important discipline every time, and we are not the only ones in charge of a project. But we can provide support and positively influence outcomes and solutions. And when we are faced with ground-related risks and complex geotechnical structures, we are best placed to understand and explain those and influence the decisions. So just beware of being overconfident, be humble, however, still stand your ground when you need to in a multidisciplinary project. So in terms of the work stages, The input requirements at each stage from each party will vary. We have these work stages that you might come across when you hear about REBA stage 1 or 2 or 3 or 4 or 5 or 6, and it gives a very good framework for people to understand where we are. Because the end goal is to achieve outcomes for our clients. So at this for this reason, the initial stage, the need is really important. It's really important to understand the need and agree the outcomes without necessarily focusing on the solution itself. This is more likely to lead to success. We then go through the different stages where we think about options. Once we come up with what the best option would be, we solve all the design issues at the design stage, and then all disciplines can produce a single coherent and coordinated output. Okay, so it's simple. The equation is simple. Successful ground engineering equates to risk and opportunity management. We're always faced with many uncertainties and unknowns. No analysis will fully replicate all aspects of the behavior of the ground and the structure. No ground investigation will quantify all the key properties of the ground. And construction will never be perfect, no matter what our clients might think, but it will never be perfect. There'll be things that happen during construction, as you see, that will be imperfect. So all that means that we have to keep the geotechnical triangle in balance. I'll talk about the geotechnical triangle a bit later. So we have to be aware of what we know versus the unknowns. What is an assumption versus reality, and what mitigation measures could be put in place. Be confident enough to ask questions, and seek advice and independent early review, peer review. And case histories. You have to study case histories. We learn a lot from mistakes, ours or other people's, but we also should learn from successes, right? So case histories are not just about things that have gone wrong, but also about things that have gone right. Because it's not always necessary to use an overcomplicated model or analysis. Simple solutions or design methods that have been proven to work could be perfectly okay. Right, so in terms of foundation design decisions, the 5 S's is a good way of remembering how to go about deciding what you do about a foundation that you need to design. Number 1, site, topography, location, and constraints. You can see on the photos, you can be in an urban environment in a very constrained site that you need to work around ancient ruins, as you can see there. That's a picture from Greece, obviously, or even in London, the smaller picture on the top left is around Waterloo Station, where we had to design foundations in a very extremely constrained space, both from left, right, and bottom, where there was buried tunnels and existing structures and access issues. The soil or ground, we have to know about the geology and the hydrogeology. Don't forget about the water, and think about the structure, the form, the geometry, the loads, and the allowable movements. Safety, such as hazards, which can be man-made or natural. You can see a couple of examples on the photos, like a karst feature, a buried underground cavity, or a bomb. And obviously sustainability, that's the 5th S, which includes environmental, social, and economic factors, right? This is a little picture from everything that you might find in the River Thames, which was part of the Thames Tideway Tunnel kind of campaign about sustainability. So types of foundations. So we've got shallow foundations, basically concrete slabs that sit on the ground and are supported by the ground. These can have different forms or shapes. and can carry different amounts of loads. We have deep foundations, commonly known as piles, of various different types and methods of construction. But you also have a foundation, which is a combination of shallow, deep, and improved ground, or the improved ground itself can be the foundation. As the example you can see here, where we have a ground mass that is densified, or an area underneath an embankment, which can be improved by including mini piles or doing a bit of dig and replace, as we call. So comparison of foundations, there's multiple solutions that could work and could support a different type of load. For example, here you can see on the left, you can see loads of 9 meganewtons can be supported by different types of foundations: shallow, deep, intermediate, but you have to think about all the other factors in order to choose which one would be the optimal or the right solution for your problem. And a new figure that has been added gives an overview of how different types of foundations can influence the embodied carbon, where you look at a shallow foundation versus a piled solution. Typically, you will hear that a shallow foundation is preferable, it's cheaper, less concrete. However, it has to be right for the structure that you're trying to support. An actual example of a situation where we had a preliminary design which considered a piled foundation for a bridge, which was due to lack of information in terms of ground investigation. You can see very few, like 3 boreholes. Literally, we could not be certain that a shallow foundation would work because we didn't know where the rock head was. However, once the ground investigation, the stage 2 ground investigation was completed, you could see that a shallow foundation would be feasible, and we changed the design to that. You can also spot that the space we had to excavate for those foundations was not sufficient to support the wing walls as well. So it was a unique design where the wing walls were cantilevering off the abutment walls. Questions to ask yourselves when you're thinking about a solution for piled foundations, for example, for shallow foundations. Would the expected settlement be acceptable for the structure? If it's too large, can you increase the size? Is there a space? But will the bearing capacity be sufficient? When you're doing, you're thinking about a dig and replace solution, a ground improvement, will it help improve performance? Will it be too extensive? Would the contractor be able to source or bring in the material, the good, better material that is needed? Or will there be too much water to deal with when you're excavating? For large foundations, again, is there enough space for deeper excavations? Will additional support be needed to carry out these excavations? Again, the water, will it be managed? If you need to pump water, will you need consent from the Environment Agency? And if you do pump it, where are you going to put it? There's a lot of things to consider. For piles, if you're thinking about large diameter piles, you need to have early engagement with the contractor to agree about whether they can actually bring in the heavy plant that is needed. Can they access the site? Is there enough headroom? Do you have temporary load restrictions? And then you go into the details of actually, how you're going to support the bore, the pile bore, and is it more cost and time effective for the contractor to have more smaller piles or fewer larger piles? These are things that will influence the decisions. So overall, we need to have a holistic approach to our design and think about the different aspects, space planning, construction sequence, risk, cost, of course, the site, and don't forget about the water, very important. The site, will be different. You're going to have differences like the ones shown in the little graphic, and the triangle. Just a little recap about this. You probably have heard it before. We're talking about 3 aspects that need to be in balance. Looking at the ground and the ground conditions, the modeling and the ground behavior, all that encompassing the empiricism and the experience that you have. And a modification is introduced to this triangle in this chapter, where everything is then surrounded by how construction process and how the key design assumptions can be verified during the works, and thinking about whether monitoring, tests, and observations are needed. So if the triangle is out of balance, you're going to have problems. There's a lot of case studies in the manual that I suggest you read. You can, the nice bedtime stories. They're almost like a story that I very much suggest you read one day, because it tells you how, even if you have the perfect ground investigation, you've understood the geology and the ground profile perfectly well, and you know everything about it. If the communication between the geotechnical and structural engineer, where you understand what is actually important for the structure, is not there, then things will not go right. They're not going to go well. You might have some of the modeling perfect, like the example of a shallow foundation adjacent to a landslip. They did a lot of analysis, but the global stability was never assessed. Or in a situation like the final case study where piles were driven in mudstone, the DES study was done, the ground investigation was done, but there was no the modeling was poor and the key design assumptions were incorrect. So everything has to be in balance if you take one thing from my talk. So I'm going to pass on to Tony now to talk about shallow foundations in more detail. Thanks.
Right. Thank you, Christina. So good evening, everyone. So my job is to give you a few highlights mainly from chapter 53, which was in the advertising, but it does depend on a knowledge of chapter 52 as well, and also a few of the other chapters which are covered. Christina's covered a few, and I'll flag up a few others as well. So you can't just read chapter 53 in isolation. That's the first takeaway. You have got to read around, particularly 52. So shallow foundations, in my view, I think they're underused and underestimated often, and undervalued. They do cover a vast scope, from very simple pad or strip footings for your house, through to larger rafts for nuclear power stations. So there's a huge scope. In terms of what I'll be going through this evening, the focus is going to be on competent soils, and particularly heavily unsolidated clays. So these might be either the stiff fissured plastic sedimentary clays, which are very common across southern England, like Galt clay, Lias clay, Will clay, London clay, and over-consolidated lodgement tills, which are very common across northern England, Wales, Scotland. So I'll be going through a few of those bullet points, okay, which you can all read there. And in terms of what's new in the 2012, from the 2012 edition, so what's new in the 2024 edition. So you'll see there's modern burn capacity theory, which is touched on. So that's VHM. This is where you've got complex load combinations. So that modern burn capacity theory is far superior, in my view, to perhaps what you might pick up in textbooks, which rely on multiple cliff sort of correction factors, which run out of steam when you've got very complex load combinations. Non-linear ground stiffness and non-linear settlement analyses. On the non-linear ground stiffness piece, it's pretty much spans my career from the 1980s, when non-linear ground stiffness first became a thing in geotechnics. It's actually still not used very often in industry, and I think it's about time it was, because if we did use it more often, I think we'd save a lot of carbon and end up with much better outcomes for our clients. So advantages, disadvantages. Well, you can read the bullet points, so I won't necessarily go through all those one by one. But perhaps the one to focus on is the one in the bottom there, in brackets. That's the one that is probably not very obvious. So vulnerable to misuse limit state codes. So I was involved in the first generation Euro codes and some of the discussions, particularly in terms of UK national application. Now, at that point, limit state codes were an exciting new thing. And we thought, well, this is going to lead to better geotechnics. And in theory, they should. There's a big if. The big if at that time was we assumed that people would use better ground investigation techniques. How naive we were. That never came to pass. So unfortunately, people are now taking a lot more focus on servitude limit state assessments. So how much a thing's going to move, which is what you need to do for Euro codes, Euro code 7 in particular. But often they don't have the data to make that analysis, do that analysis properly. So then it all falls apart. So as a real problem, particularly for shallow foundations, because for shallow foundations, to make the right choices, you do need to make a good assessment of how much they're going to settle. That in turn needs better quality ground investigation data than is often available. So that final point in brackets is very important, because I've certainly seen a lot of misuse of limit state code. Another strapline here. So think global before local. It's very easy, particularly as a younger engineer, when you're given a job to do in terms of design a shallow foundation, is to get excited about doing a burn capacity check, then you get excited about doing a settlement analysis, and that's great, because you'll be using a lot of stuff you've learned at university. Well, university has gone through the right things, hopefully. But there's a lot of other failure mechanisms that might develop depending on where the site is, what's the topography, what has happened at the site before. The UK, for example, has a rich history of mining. Most parts of the UK have been mined or quarried at some point in their history. If you haven't got a depth study, for example, you may not know about that. So then you could easily get into big trouble. So you've got a solution feature there in the middle there. Something that bedevils the insurance industry in the UK, particularly in southern England, is the effect of high water demand trees, seasonal shrink as well. There's a whole industry that gets involved in that stuff. So for example, if you take over a site that was a woodland, somebody's developers chopped all the trees down, don't be surprised if all your foundations go up instead of going down, because they're responding to the fact that the ground's been desiccated. And then another thing which can trip people up is the bottom one, where there's been a large cut fill. The problem here is often these happen in different contracts. So there might be a preliminary contract which levels the site off involving cut and fill. You may get involved in a second contract that follows up and for doing the building design. So, that whole sequence of activity is very important that you know about. The other problem here as well is in terms of the bottom line there is often these sort of deformation failure mechanisms are not considered within commercially available software. The software might help you do a settlement analysis, but it won't necessarily help you with some of these other issues. So again, if you're not aware of those, you could end up in serious difficulty. So you do need to take a big picture appreciation, if you like, of what's happened to the site, both in its history and its current state. So this is from chapter 52, these images. Obviously, if you're going to do shallow foundation, first of all, you've got to have a stable excavation. And if the groundwater table is above the base of the excavation, you've obviously got to get the groundwater in control. Because obviously the very important point here around safety, people have got to go into the excavation, so they've got to be safe. That's the first priority. So there's quite a few things to think about there, depending on how deep the excavation is and what the materials are. Battering back might be suitable. You may need some form of temporary retaining structure. In the right-hand image there, you've got groundwater control issues. Quite often groundwater control can cause big problems because main contractors might think groundwater control just involves keeping the excavation dry. So they might think it's fine just to have some pumps in the bottom, which is, pumps in the middle of the excavation somewhere just to pump the water out. That can actually create a serious problem if it pulls in fines while they're pumping the water out, and actually lead to large scale instability. So, for example, a few years ago, there was a major collapse in central Cologne in Germany because the contractor was pumping from inside the excavation, which pulled in fines. Several people killed. Building outside the excavation collapsed as well. So, the issues around how do you do the dewatering, usually it's better if you can do it outside the excavation. Needs serious consideration and careful specification, because often that needs specialist, for example, groundwater contractors to be involved, which wouldn't be in the sort of spectrum of expertise of a main works contractor necessarily. Again, in terms of when you start to get into analysis, again, it's about thinking global before local. So, often people might get drawn to what's happening beneath an isolated footing, but then forget the fact there's lots of isolated footings, but working all close to one another. So you might have to take account of what's happening beneath the whole building. Okay. That might, as indicated in the right-hand side there, lead to large stress increases to perhaps a softer, more compressible layer at depth, which might be far more onerous than the situation on the left. And those interaction issues start to get a lot more severe if there's lateral loads involved as well. So you need to think about, the site, the adjacent structures. As Christina mentioned, often you're building these foundations in close proximity to existing infrastructure, and then the overall topography, not just what's happening within your site, but what's beyond the site boundary. It might be a slope, for example. Now, this is probably, the next few slides are probably the most important bit if we're going to have a more balanced approach to designing shallow foundations. And this is around the topic of reliable foundation movement. Often as geotechnical engineers, if you ask the question, the structural engineer will say, oh, 25 millimeters. I hear that, not just in the UK, but all over the world. 25 millimeters. Sometimes they'll say 1 inch, which is what they'll do that in the United States. As the quotes, the first quote is from Professor John Burland, and it's absolutely true what he's saying there. When you start to ask the question, well, why is it 25 millimeters? Often there'll be silence, but that's what we always assume. Sometimes people will say, oh, well, we've done an analysis of the superstructure and this is what it, but again, the second quote comes in, because when people try to do this type of analysis using the types of models they'll use for the superstructure. What they don't take account of is the sequence of construction, how the stiffness of the superstructure itself evolves, how the stiffness of the connections evolve, and the displacements that take place during construction, how that all evolves. So what you'll end up with is ridiculously large locked-in stresses in the structure. So, inappropriately low allowable settlements is the thing which usually inhibits wider use of shallow foundations. At the end of my bit of the presentation, I'll go through a case history, which was a particular issue. Now, the key thing is that structural damage will only occur due to differential settlement within the structure, so angular distortion. The total settlement is almost irrelevant in terms of the structural performance itself. It'll obviously affect things coming into the structure, but they can usually be quite easily detailed to accommodate relatively large total settlements. So the graph on the right-hand side, that's taken from a survey of actual performance of buildings. Now, hopefully you can see we've got maximum settlement on the bottom and maximum differential settlement on the vertical axis. And you'll see there's some big numbers here. So we're going up to 400 millimeters, okay? And the open circles is where there was, or the open triangles is where there was no discernible damage in the structure. Then when you've got a solid infill, there's moderate damage, and where there's a cross, there is severe damage. But what you'll notice is that 100 millimeters maximum settlement and 50 millimeters differential, the vast majority of buildings performed perfectly adequately. So that's one of the key takeaways here. And this is for frame buildings on isolated foundations. Rafts are much more robust again. And the corresponding figure, 5210A, which is for rafts, shows that they will usually accommodate far larger settlements with no damage if the raft's designed properly. So the histograms on the right-hand side, this is from a more recent surveys. Studies are done through the 1980s to early 2000s. So there's hundreds of buildings. The buildings is for the top, bridges for the bottom. So there's hundreds of case records here. This is not just an isolated one or two or a few dozen. There's literally dozens and dozens of case records here of building performance. So this is actual behavior. It's not theory. And here, for virtually all the cases where the settlement was less than 50 millimeters, there's no discernible damage. It's only once you got beyond 100 millimeters total settlement you started to get cases of excessive movement and damage. So in table 52.5, there's a summary given, but some takeaways is for pad strip footings on clay. 65 millimeter total settlement is a good routine limit. For sand, it's a little bit lower. The reason for that is differential settlement is more of a problem usually in sands, and usually that movement obviously occurs that much quicker, which is a more damaging form of movement. Now, these are routine limits, and these are okay for routine structures. But if you're for more special structures, put it that way, it's much better to use angular distortion as a measure of differential movement. And again, there's limits for those given in table 52.6. So, for example, a common SLS limit would be 1 in 500 for frame buildings. So that equates to a 20 millimeters differential across a 10-metre span. So if you start using all those sort of numbers, a lot more meaningful. It's the first thing, and it's the case that you'll probably more often than not get shallow foundations to work if you're on competent over-consolidated clays, which we often see across the UK. For bridges, the bottom figure is relevant there. Now, for site-specific assessments, you could start to think about the sequence of construction and when those movements will develop. Because the reality is a lot of the movement which will occur, a lot of the settlement which occur, will take place during construction. And most the components that people are normally most worried about are the actual finishes. So things like the cladding, which will go on right at the end. By that stage, a lot of the settlement has actually already occurred. So it's only the movement which takes place after those sensitive components are built into the structure, that damage to those elements can occur. It's logical, isn't it, when you think about it? But often people don't go through that thought process. So this sort of sketch on the right-hand side goes through that sort of conceptual thinking. So you could think about when things are going to get built and which is a component that is sensitive to movement and when's it going to get built. So, for example, things like the internal machinery, lifts, escalators can be sensitive, but they're the things that will go in right at the end of construction, by which time more than half of the settlement has probably already occurred. So just going on now in terms of burn capacity. Again, this is a source of confusion sometimes amongst project teams, because usually when you ask the question, the structural engineer will give you gross burn pressure, but obviously we know as geotechnical engineers, or we should know as geotechnical engineers, it's net burn pressure, which is what the ground will respond to. And that's something you'll need to assess, because the structural engineers probably won't give you the net burn pressure. And that's very straightforward to do, but you just got to remember to do it. The new section on modern burn capacity theory, that's really around where you get complex combinations of vertical, horizontal moment loads, or where undrained strength increases very rapidly with depth. So I won't be going through all those equations. They're all there in the manual. But some of the main implications I will cover, and it's summed up in this slide really. So the first takeaway really is conventional theory can be inadequate. So as the load inclination increases beyond about 18, 19 degrees beyond the vertical, conventional theory in terms of all those correction factors, there's a whole long list of correction factors you start to have to apply, and they start to break down. So that's when you need to start thinking about using more modern burn capacity theory. The other key takeaway is that if there's just one-way eccentric loads, so this is the effective width method, that's actually not too bad. That actually compares pretty well with more modern rigorous theory. But obviously these days, and again, it's another outcome from limit state codes and limit state analysis, is we end up with some very complex load combinations these days. So usually you'll end up, if you've got wind loads, an impact load, etc., you'll end up with two-way eccentric loads. So you've got a horizontal load this way, horizontal load that way, maybe an overturning moment. So then you'll end up with what's usually referred to, rather than the effective width, the effective area method, which is shown here. Now that doesn't bear any real scrutiny at all, and it's wildly inaccurate. So the simple problem, when you look at some of the papers, unfortunately, on modern bearing capacity theory, it all comes across as being quite complicated. But the simple image is that if you've got two-way eccentric loading, effectively the contact area goes across one of the long diagonals. You basically underestimate the contact area. So if you've got a mental picture in your head, that's it. You know, the effective contact area is much bigger than the effective area method would indicate to you. The other piece to take away is the impact of embedded foundations, and that's really summarized in these two images. So this is a little bit complicated. But basically what you've got on the vertical axis is a normalized moment load, and on the horizontal axis you've got a normalized horizontal load. Okay, so you've got a horizontal load divided by the ultimate horizontal capacity, and on the vertical axis you've got the applied moment loading against the ultimate moment resistance. Okay, and then on the V over V ult, that's basically depends on the amount of vertical loading that influences the overall capacity under that VHM loading. And you can see the standard theory is the dashed line. The modern theory gives you the solid line. You can see it's higher, but that's for surface foundation. But of course, virtually all our shallow foundations are not on the surface. They're embedded, often, you know, 1 meter or 2, and that embedment relates to the size of the footing. So if you've got say a 2 meter wide footing buried 1.5 2 meters, which might be fairly common, that gives you a huge additional resistance. That's shown on the right hand side. So again, the classical theory, the stuff you'll find in a lot of undergraduate textbooks, is the dashed line. The solid lines is what you'd actually get, and the modern bearing capacity theory gets you more into that position, and that has a huge beneficial effect. That's basically because the cross coupling that occurs between horizontal and moment loading is ignored in the classical theory, where you've got these independent correction factors. Actually, they're cross coupled. So now moving on to settlement, which is, as I mentioned right at the start, is often the most critical consideration. Now there's lots of different methods available, from simple to complex, and I'm not going to go through all those in too much detail. But irrespective of the method, probably the most important thing is the choice of the deformation modulus you use and its variation of depth. So this comes back again to your quality of ground investigation data, and maybe a few SPTs aren't going to cut it for you. And as Professor Berland discusses, and he discusses this in one of the earlier chapters, chapter 19, if you can make the correct choice of modulus, then actually the simple one-dimensional method is a whole lot better than a lot of apparently more complex methods. And that's shown on this right-hand graph. The one-dimensional method is shown in the solid line, and the other methods are shown in dashes. Now, the reason for that is because real heavily over-consolidated soils, and we're talking about over-consolidated soils here, they've got stiffness anisotropy. That means the horizontal stiffness is quite a lot higher than vertical. You've got stiffness non-linearity, so small strain stiffness is perhaps an order of magnitude higher than a large strain, and the stiffness increases with depth. So all those real facets of behavior mean actually, despite its simplicity, the one-dimensional method, simple as it is pretty good. The big if is, can you make the right choice of stiffness modulus? So just go into that a bit more detail. So on the right hand side here, we've got a graph, and these are actual measurements of settlement below. In this case, it's a raft foundation. In fact, these are measurements that were made for a project in Germany, and there's a lot of similar data in the literature as well. This is for glacial clay, increase in strength, stiffness, of depth, but you'll see the same sort of data for plastic fissured clays as well. Now, for the near surface, so that's the depth, that's the brown line. For the depth, we're in a 0.2b of the raft in this case. That's where you see relatively large vertical strains developing. 0.2b obviously is very shallow relative to the size of the raft. So for example, if you had a 5 meter wide footing, that means that most of your settlement, or a lot of your settlement, is taking place within the top meter. Once you go beyond that, at greater depth below 0.2b, you're at very small strains, less than 0.1% strain. So that's small strain. You won't measure that in the odometer test. That's outside the accuracy of what you can measure in the odometer. So if you're taking account of what you're getting out of odometer testing to 20 meters depth, you'll end up with the wrong answer. It's as simple as that. But that sort of theoretical issue, if you like, has a lot of practical implications. So first of all, your ground investigation needs to focus most critically on that near surface zone. So that's where you need to intensively investigate the area. The second important practical point is construction control, and this is what Christina mentioned, and Manos will pick up on that in a lot more detail after me. So from a practical point of view, your construction control and verification is important, because that near surface zone gets disturbed, then you might have done the most wonderful settlement analysis, assuming undisturbed conditions. But of course, if that surface layer gets disturbed, well, all bets are off, aren't they? So you've got to have control over what happens on site. This is another point around the so what, practical consequences. So empirical correlations, you'll all see all sorts of empirical correlations given in the literature. Most of those, certainly most of those which are common use, date back a long time. You know, the EOSU values that you'll see quoted, maybe numbers of 200 might be familiar for drain stiffness, 400 for undrained stiffness. Those numbers came out of work which I was familiar with just after I finished at Imperial College, which was a long time ago. That was in the 1980s. And that was well before anybody thought of doing finite element analysis routinely. Now, in those days, when we used to do hand calculations, we simplified everything. And that's what the back analysis was based on. So as soon as the stresses dropped off to less than 20% of the initial vertical overburden stress, we stopped calculating settlement. We said, that's it, we can ignore the rest below that. So if you now use those old-fashioned correlations in a modern analytical method, where you keep on calculating settlement below that threshold, you'll end up with, well, I was involved in an expert witness case, and one of the other experts actually did that. You end up with double the settlement often. So you won't be close. So you need to recognize, when you use empirical correlations, you need to recognize what was done when that empirical correlation was derived, and then do the same type of calculation. If you chop and change using the old correlation in something different, you'll end up with the wrong answer. And all those graphs explain why that is the case. So there's a little summary here. Just to take away is Skempton and Burham really is considered obsolete. I still see people doing it. The new chapter 53 gives you a summary of nonlinear methods. There's 3 main simplified methods there. They are relatively rapid to use, and they avoid finite element analysis as well. But if you do find, or you think you do need to use numerical methods, so finite element analysis, then actually you need to think about why you're going to do that. There's a SUI report on the topic, SUI report C791, and there's a process there called the 10 steps. And the first point is you've got to have a clear objective about why you're doing it. You know, I quite often see these days people using finite element analysis, but they don't really have a clear objective of why they're doing it. You know, what's the added value? Often there isn't actually a lot of added value. So think carefully before you do it. Sometimes when you've when you've got particular situations, it is worth doing, but then you need very specialist, skilled people to do it properly. I'm fortunate to work with a few of them, but you know, it is a very specialist activity. Just on elastic methods, you know, displacement influence factors. There's a lot of elastic methods in various textbooks. A lot of them aren't actually very good or very appropriate, because they either assume a constant Young's modulus for depth, which is seldom appropriate for UK conditions, or they assume that the compressible strata is an infinite thickness. Again, that's not appropriate. But in chapter 53, there is a method there which you can use, which makes more appropriate solutions, more appropriate assumptions. They are useful for very quick, simple, you know, order of magnitude estimates. So they are useful, but you just got to choose the right one. So this image gives you an idea. Right, I'll close it up. Right, okay. So this gives you a quick idea of you know, the thinking you need to go through before using a simple method on the left-hand side. You know, if you've got good local experience, simpler design objectives, or lower level of risk, or whether you want to use, if you've got more complex objectives, then that's when advanced methods are more appropriate. So how long have we got then, Ben? 0 time, or 5 minutes, or 2 minutes? Just finish up. Okay. Right. Okay. So I won't go through this. This is about case histories. But the slides will be made available, I guess. Yeah. Okay. So the slides will be available. So just a bit on case histories. This gives you a very quick feel for the ballpark of what you might expect. So the information is in the chapter. And this case history, which actually picks up a lot of the points I've just gone through, is actually in chapter 53. So I suggest you read it, because it's in probably 3 pages, summarizes a lot of key issues I've just gone through. And just one thing that I'll emphasize, and probably was the most important step here, was the original settlement limit was a total settlement of 5 millimeters. That would have been completely unworkable. Whereas I renegotiated a more rational objective, which was a time-dependent angular distortion of 1/1000, which was all around those glass panels and the movement there. And because of that renegotiation, everything else was possible in terms of using shallow foundations. Whereas in this example, if you use piled foundations in these ground conditions, which was a bouldery lodgement till, piling would have been a disaster because of all the problems that would have arisen on that. Right, there you go.
Hello, everyone. So in the next slides, I will focus on the geotechnical triangle and mainly on the importance of the fifth component mentioned previously with regards to the construction process and the design verification. I'll try to demonstrate, referring to a few case studies from my construction experience, how we as geotechnical engineers can help to keep this geotechnical triangle in balance through observations, geological inspections, field testings, and monitoring that can be done during the construction works. In some cases, the information that we collected from site were used to feed back to the design models and analysis, and either optimizing the final solution was implemented on site or allowing the construction works to progress without any delays. As per the manual, often several important design assumptions have to be made in order to proceed with the design, and we need to verify these assumptions while we are on the construction site. I'll now present the first example, which relates to a 60-meter long 3-span integral bridge. In that case, a pile foundation, as you can see on the top screenshot of the model, has been considered for the bridge piers, while a cast in situ spread footing has been designed for the abutments. Now, one of the main design assumptions for the south foundation was related to the presence of unweathered mudstone at the base of the abutment excavation, with a minimum required unconfined compressive strength of 2.5 megapascal. Through relevant design drawings and specifications, these design requirements have been communicated to the main works contractor. There was also a relevant note for the requirement of a field verification by an experienced ground engineering professional. So referring back to the geotechnical triangle, what we needed to achieve in that case is clearly to verify the key design assumption. During the construction work, it was proved that at the specified formation level, it was close to the interface between the weather and the weather rock. And as such, the rock was typically recovered as a gravel-size rock lumps that could be crushed between finger and thumb. And according to British Standard 5930, this actually correlates to a weak rock with a maximum UCS of 1 megapascal. Therefore, the selected and implemented solution on site involved further excavation and re-inspection at 500 millimeter intervals, enlargement of the excavated area, and backfill of any over-excavated volume with a general purpose ST1 concrete. Picture on the bottom illustrate the blocky nature of the rock that was recovered at the final excavation level, which sits approximately 1.2 meters deeper than the original specified. Based on field observation and description of the rock strength, in line with the British standard mentioned before, the rock material at that level has been described as very weak, taking also into account the enlarged excavated area, the installation of the general purpose concrete, and revisited design analysis. The cross-section on the left illustrates the solution that was finally implemented on site. The next few pictures show the enlarged over-excavated area. You can see on the right-hand side, and then left-hand side is after the installation of the general purpose concrete. The next case that I will talk about is related to an embankment foundation on improved ground. This is for a 4-meter high approach embankment towards an overbridge. The anticipated ground condition at that specific area consists of 2-meter thick alluvium, followed by weather and unweathered rock formation. All these were actually verified during the construction works as part of the regular geological inspection that we have completed. Also, the design requires for a 2-meter excavation and replace zone due to the presence of the alluvium mentioned before, and the minimum undrained shear strength of 75 kilopascal at the bottom of the dig and replace. That was quite straightforward to validate on site through hand shear vein test, considering the presence of the unweathered rock and the locally exposed weather formation. Based on the available GI information, though, the groundwater table was expected to be slightly below the dig and replace formation level. However, groundwater ingress was actually observed from the bottom part of the excavation, leading to its flooding. Without that was made challenges for the construction work and the team to install the relevant lime stabilized material that form part of the dig and replace zone. Based on this site observation, it was agreed for a 500 millimeter thick extension of the dig and replace zone. This was constructed with the use of free drainage 6C granular material in order to form a starter layer, followed by the installation of separator geotextile on the top, and consequently allow for the installation of the specified lime stabilization material. On the other hand, there are occasions where site observations and field testing can facilitate optimization of the final solution that we implement on site. In that specific case, a minimum 2-meter thick dig and replace zone underneath a 7.5 high approach embankment was specified, considering the available GI information and the expected ground conditions. This dig and replace zone was required to ensure compliance with the project specification requirements, which are mainly related to the differential settlements. During the site geological inspection, the competent strata was actually encountered at a shallower depth. Also, the field testing proved that the CU compliance at the reduced depth. Therefore, following revisited of the relevant settlement analysis, the above on-field, the aforementioned on-field findings allow the reduction of the dig and replace zone to 500 millimeter, and in that way optimize the amount of volume of the lime stabilized material that was used on site. The next case study relates to a pile foundation of a underbridge. This is a 90-meter long structure with a 19-meter wide clear span that was founded on 122 board piles with 1.2 meter diameter each. What was particularly challenging in that case was the presence of a geological valley at the location where the underbridge was constructed. What you can see over here is the geological section at the location where the underbridge was constructed, along the whole extent of the underbridge. And what we can clearly notice is the fact that the rockhead depth varies significantly, while the second challenge lies with the uncertainty over the exact thickness of the rock weather zone. Foundation design in that case requires for a pile embedment of 3 times diameter within the competent unweathered rock formation. So we're talking about 3.6 meter at least. And that requirement had to be validated either prior or during the construction works. In collaboration with the contractor and the piling specialist, it was agreed that the geological inspection of the pile arising will take place to ensure compliance with the above requirement. And that was in order to verify the design assumption with regards to the rockhead level and the thickness of the weather rock. Focus was given on the very first pile that was installed, where according to the inspection and test plan of the project, all relevant parties, including the designer, piling subcontractor, and the contractor, were present to witness the recovered soil during the pile arising. And at that point, it's worth to highlight one specific section from the manual, based on which throughout the process of design assumption verification, it is important that the key assumptions are communicated to other parties, so that ultimately this assumption can be checked when the foundation are being constructed. And this is exactly what takes place on the specific occasion and all the examples I shared with you previously. Now, as part of the geological inspection of the pile arising, the site observation actually did validate our design assumption. And the following pictures illustrate all the geological formation that were witnessed during the pile arising, including the glacial till, glaciofluvial deposit, the sandstone and the mudstone part of the rock formation, which provide the necessary confidence on the minimum pile embedment that was actually achieved on site. Top right is an extract of the inspection and test plan, ITP. The ITP is a project document that outlines the necessary inspections, test and quality control procedures for a specific task, aiming to ensure compliance with the standards, the specification, and the design requirement. This specific section presented here relates to a geological stratum identification during the piling works, finding of which were recorded on the form showing on the right-hand side over there. And this form, among others, captured the criteria under which the designer site representative should immediately be notified by the piling specialist. And the purpose of this task was to ensure verification of the design assumption for all the piles that were constructed in that area, considering the variation of the rockhead level as mentioned previously. Working pile tests were also carried out for the specific underbridge foundation. Picture on the left shows the reaction piles on the four corners, the hydraulic jack located on the top of the tested pile, and the steel frame used for the load transfer and application. The working pile test actually verified the pile performance, the fact that the pile meets the required load settlement behavior criteria. As per the graph on the right, the pile was tested under the working load and 1.5 times the working load conditions, and the test results demonstrate compliance with the permitted settlements. Worth to highlight at this point the high cost of the field verification, specifically working pile test, and the fact that as designer we shall be prudent when we specifying such tests, and things like the ground complexity, availability of previous pile test data in similar piling techniques, and experience of piling in similar ground can all inform decision with regards to the necessity of such test on site. And this is the last case that relates to field testing of embankment foundation. The project specification requires for verification of a minimum value for the modulus of deformation EV2 at the embankment formation level. And you can see the different techniques that were used on site to validate these assumptions, from plate load test to more sophisticated Dynaplug or even geophysics techniques on the right-hand side. Yeah, thank you.
Okay, so thank you to our speakers. That now brings us on to our Q&A part of the evening and discussion. So, oh yes, do anyone have any questions in the room before we go on to the online audience? Yes.
Thank you for the great presentation.
Oh. Perhaps if you give a name and affiliation.
Hello, Brian. I think the mic's not quite working.
Okay.
Check, mic check.
It should have been working.
Oh,
Check now. Okay. Just use turn it on. Good evening, everyone. My name is Jandas or Aslan from Senior Engineer from Watt McDonald. Thank you very much for the great presentation for the evening today. So I have a question maybe for Tony. The question is, how much of today's foundation practice is truly driven by soil behavior, and what breakthroughs in advances in site investigation or sensing are we still missing to make that a reality?
Well, okay, so obviously the soil behaviour is fundamental for us making the right choices, isn't it? But in terms of the ground investigation techniques, I would say that a ground investigation technique which is very powerful but very much still underused are geophysical methods for determining shear wave velocity, and through that G0 or Gmac, that very small strain stiffness, because that gives us an anchor point of which to make more rational choices in terms of what I mentioned, in terms of getting the right choice of deformation modulus, because there's a whole huge body of data now in the technical literature where we can make use of G0s to assess the mobilized stiffness at a range of larger strain amplitudes. So for me, if industry focused a bit more on making G0 measurements, we would end up with better foundation design, I think, going forwards.
A question for Manos. In the first case history that you showed, where you had to dig down another 500 mil, another 500 mil, I think it's like 1.3 you had to go down extra. Should the ground investigation or the design have highlighted that earlier on. Should it have been picked up, do you think, or was it just a risk that was always going to be there and had to be verified on site?
I believe it was mainly related to the exact level between the interface of the weather and the weather zone. So it was unlikely that it was actually around that level, the specified excavation. So in that case, it was a geotechnical risk that was actually confirmed on site during the works, and we have found this way to overcome, let's say, the issue and reach the appropriate UCS for the material needed.
Hi, Rory Cripps, engineering hydrogeologist for Mott MacDonald. Question for Christina. Talked about communication being very important. Would you have any tips or tricks for speaking about very technical stuff to a client who might not be as technically adverse in aspects of the project?
I suppose the easiest way is to think about simplifying it and not going into, a lot of technical details, but trying to get the client to kind of visualize the risks or the uncertainties, the considerations that need to be taken for the design. Bringing in the client in decisions or the disciplines that are involved in a project early on as well, and the contractor or the specialist contractors that will build the works is quite valuable as well. Having some kind of progressive communication where things are discussed and decisions are made, considering what is important for each party at each stage, will help you get a better outcome. And understanding why somebody wants something, what is the reasoning behind certain requirements, you can find the right balance. There's something that somebody told me, which I like to say often, that in a situation like this, when you have an architect who thinks the end product is the most important thing, you have the client who wants a certain outcome, you've got a geotechnical engineer who's worried about the ground or the groundwater. Everyone has a point to make, so you need to find the right balance and understand, what can give every time. I suppose it will be a compromise from everybody.
Thank you. Thank you for the nice presentation. Saso Kanasabet from COVI, ex-MOGE as well. So question to Tony. You already answered to the first question. This is about predicting settlement using nonlinear method. Yes, it will be more accurate, but that it requires more testing, for example, seismic CPT or advanced laboratory testing to establish these nonlinear curves. And then, of course, as you mentioned, the construction control to make sure that doesn't disturb the ground. But then when we go with the simplified method, 350 CU or 600 CU, but when it comes to the performances based on the differential settlement, would that make much difference in terms of the foundation design?
Well, yes, it can do. I suppose I don't want to sound them just advocating a more sophisticated approach all the time. It's really if it's going to make a difference or not. So if you can use a simple approach and you're going to end up with a reasonable design, then that's fine, as that sort of image showed, or I suppose thinking through the process, if you were to use a more sophisticated approach and you ended up with the same outcome anyway, it doesn't make a difference, does it? But the issue is that often it's where you have these situations where it does make a difference. And that's where the more sophisticated approach can be of huge benefit. In terms of differential settlement, you've got to be careful with conventional linear elastic methods because it can underpredict differential settlement, particularly if it's from a lightly loaded to more heavily loaded. So say if you've got several pads with different degree of loading, one's more lightly loaded, one's heavily loaded, you find that non-linear methods might actually give you a bigger differential settlement. In terms of the worry about greater parameters, what I'd say is there's actually quite a lot of good, if you like, empirical relationships now, which are available in the literature, where, you know, if you know the G0 value, or you can make a reasonable estimate of G0, and again, there's some good modern correlations for that, together with some of the more basic characteristics of the material in terms of classification test data, you can actually make a reasonably good stab at what the non-linearity is going to be. You know, so there's several publications now which summarize that. So, you know, that can get you a long way without having to do very sophisticated testing in every site.
Thank you. Thank you all for very nice presentations. My name is Rishabh. I'm from UCL. I have a simple question. Working in a multidisciplinary project, as Madam said, we have to take our stand as well, but we need to keep also in mind that there are other specialties as well deployed. How do we convince the project investors to invest in ground investigation? How do we decide how much we want to spend on board logs and how much?
Yeah. Okay. So, well, as Christina mentioned, it's all about outcomes, isn't it? And you got to. There's no use talking to people about the technical detail. As a client a few days ago said, don't talk about pore pressure. You got to talk about, you know, what are the cost issues. You know, is there potential to save a lot of money? Is there potential to save a lot of time? Is there potential to reduce risk on the project? Is it going to be safer? So you've got to boil it down to those sort of issues. So it really becomes, you know, the business case is one side, risk management. Yeah, and that's how you're going to justify it. So like that case history was really, and that was fast track design build. So there wasn't a lot of time. The contractor didn't have a lot of money for sure, but he also was facing huge liquidated damages for that building project if he was late, and there's a good chance he'd be late if he went down a piling route.
Okay.
So can I add to that? So using the question that Peter asked about that particular foundation, so that is a good example of, yes, okay, you can do, you know, 2 boreholes on either side of the bridge or whatever and get a perfect model, or you can have whatever it is that you have and then decide on whether the risk of not having those 2 boreholes and understanding exactly where everything is along the foundation is too high, or it can be mitigated with the solution that Manos kind of presented, and whether the contractor is willing to take on that risk and have all the mitigations in place and be prepared to manage it versus mobilizing a rig, for example, for a ground investigation. So it has to be thought about in that context as well. But generally, your question, I love it. It comes up in every single presentation I've ever been in the last 20 years that I come here, about how do we get our clients to pay for the ground investigation. Yeah.
Just on a similar theme, I suppose, with the case study you were talking about, Tony, the Newcastle Library. Apologies for cutting you short there.
No, that's all right.
Did you need to persuade the client as part of your negotiations that they needed more monitoring for the to?
No. It was really the design build contractor. You know, the ultimate client wanted his building.
Yeah.
He wanted it on time. And obviously the contractor wanted to avoid liquidated damages, which were punitive. Whereas for him, foundations was the ideal solution because it took out a lot of risk and was quick.
And I saw as you were flicking through your slides, there was a block sample there. Was that for the same
Yeah.
case study?
So we
a lot of testing to get that. Good
so
quality.
we dug a few pits, took some block samples. This was while there was an old building which was being demolished. And then we did some CPTs after the demolition was complete to just check, it was reasonably, where we did the pits was reasonably representative, and there wasn't too much variability across the remainder of the site.
Yeah.
So it worked well.
We were discussing this. Sorry, because carrying on. We were discussing this before coming here as well, and I think you mentioned that it was also about asking why is this settlement criterion set? Why? What is your need for setting a very, very tight settlement criterion, which then helped inform the future decisions, which was all about the cladding, right? So understanding the why is also important.
Yeah, and sometimes you've got to be quite assertive, I would say. So you got to be got to push quite hard sometimes.
So we've got a question in the room. There's one online as well. Yeah, perhaps. Oh, sorry.
Yeah, thanks. Nice presentation. My question is kind of asking Manos. You mentioned about the integral bridges, 60 meters or so. And one of the issues are you try to keep everything fixed on both sides of the abutments together. So kind of behavior-wise, you've designed it to standard. Now, in relation to monitoring, did you actually think about what monitoring you're going to get in terms of the deformations that's going to take over that 120-year design life of it? And what sort of consideration did you allow for differential temperatures on the bridge deck as towards the abutment side?
I think that would be a question mainly for our British project director. So
I think that goes beyond a little bit our expertise in terms of the bridge deformation and whether there is a need for structural monitoring or not. But you're right, like integral bridges are a very interesting topic of discussion, and how the foundation design affects the structure. It needs to work with the structure. We didn't necessarily go to that level of detail for that one.
How did you set the limits in terms of the deformation? Because you have definitely a soil structure interaction.
Yeah.
At the same time, you also have a temperature. I do know.
There's a specific way to check and design the integral bridges. I think for this one we did follow PD 96694. And then there are certain differential settlement or differential movement criterion set for adjacent supports of the bridge. And they are set by the structural engineers depending on the performance they want to achieve, and it depends on the deck and the construction of the deck and how the deck behaves and the beams and all that. So there was a set criterion. We did work on a differential settlement criterion between adjacent supports for this bridge.
Thank you.
Does that answer the question?
No, I think what I was trying to get was definitely it's 120 years. We all know the design life. So if you have deformations taking place, you must kind of monitor that deformation to be a lower bound theory, a lower limit to a higher limit, and where you actually pictured that deformation, or did you allow for that in some format? Because it's also fixed at either ends. So it is a portal frame structure.
Yeah.
We got to control that. But if that limit moves over that range, of course, we can't say, it cracked or whatever that liquidation damage is. So what I was trying to get is whether someone did actually specify the monitoring that needed to go into it, because it's quite new, the concept of 60 meters integral.
Maybe I'll make a point that I wasn't involved in the design at all, but I suppose the question I'd raise in terms of monitoring is, before you do monitoring, you've got to think about what are you going to do with the monitoring data.
Yeah.
You know, so, you know, in that situation, the guidance was followed. And, you know, in terms of structural analysis, there was obviously trying to bound the locked-in stresses, which are getting induced in the deck. And I think there was confidence that, given the sensitivity studies which were done, looking at different combinations, there was, you know, a comfort zone that the structure was working in. So I think if you're going to do monitoring, you've then got to persuade the client that you need to do that monitoring over a prolonged period of time, which then would raise questions. Well, aren't you confident about the performance of the deck in the first place? You know, what would you do with the monitoring data, or what would he do with the monitoring data, say in 10 years, 20 years time?
Thank you.
We've got one question online for Manos. In the second case study where the excavation was flooded, why was class 6C used instead of the class 9J that was originally proposed for ground improvement?
Because the 6C material is much easier to be placed under, let's say, this sort of conditions where we have groundwater present. So it was, constructability perspective, it was way much easier for the contractor to be able to place that material on the over excavated 500 mil that I mentioned.
Okay. We've just had one more online, but I think we've slightly overrun. So perhaps is there one more in the room, please?
Question is beyond this early career group topic is how do we help or ensure early career engineers to develop judgment, not just the proficiency?
Yeah, so what I would say is to ask questions and be interested in understanding the bigger picture. Don't settle for, oh, I'm going to do a little bearing capacity check. There you go. The utilization is less than 100% good. You need to be able to understand the bigger picture, and if that's not given to you, then ask for it and try and kind of understand what's going on before and after your little bit that you've done. That's my thought on that.
Don't forget the water.
I said that many times, didn't I? Don't forget the water. Yeah.
Maybe I could add to that, and it might come across as being a little bit brutal. It's not meant to be. I think young engineers have got to help themselves to develop judgment. You've got to. I think one of the ways of doing it is studying case histories, understanding what's worked, what hasn't worked, and then if you're a designer, showing an interest in construction means and methods. I used to try and through these sort of events, getting to know local specialist contractors, give them a ring, ask them questions about how far does this piling rig go, why does that dewatering well work like that. So you get a feel for what works at a practical level as well as a technical level. So it's all about trying to balance, I suppose, technical rigor with pragmatism. Weighing up the evidence in terms of what's good evidence from what might be unreliable, and then making your choices. That takes effort, doesn't it? So it's not going to be given to you, and doesn't just come with experience, in inverted commas. There's a lot you can do to fast track the development of that judgment. Hopefully that doesn't sound too brutal. It's not meant to be.
I think that's an excellent message to end upon. Thank you. Thank you.